Okay, we're now recording. All right, I was actually done with yesterday's stuff, 3.7. In fact, I'm throwing one problem out, by the way. So let me get that out of the way. 3.7, let's skip problem 17. So it was 7 and 19. I did many of them. I don't really like 17 after all, so please throw out 17. Okay, so again, 3.7, skip 17. We're on to 3.8. It should be a topic you've seen before in pre-calc, maybe even in intermediate algebra. Okay, so hopefully this section will not be too bad. It involves exponential growth and decay, right? So exponential growth and decay problems is what we're up against for today for 3.8. Okay. All right. So here we go. This is quite calculator dependent, so you want to have your calculator handy. You can have your calculator ready. All right, so 1 through 11 and 19, they're all word type of problems. So on page 242, there's question 1, 3, 5. Again, I don't keep it up that long because you can always look at the video later if I'm going too fast. And if you have the book, you can just look at the book. Okay, 7, and there's 7, 9, 11. Let's see, 11's got a lot of reading there. Okay, and then what do we have left? 19, was it? 19. Yeah, okay. So that's that. All right, so exponential growth and decay on page 237. Okay, number 1, you can put that on your cheat sheet. dy dt equals ky, although it's not as important as number 2, which I'll show you in a second. But dy dt, the rate of change of some substance is proportional to the amount present. That's the language that you would hear. Okay, so rate of change is derivative, dy dt, is equal to k times y. You might remember doing proportion problems in algebra. Okay, so it's proportional to the amount present. So a lot of naturally occurring items either grow or decay in this fashion. Okay, so what's the rate of change? Well, it depends how much is already there. So if you have a population of anything, population of bacteria, of animals, of people, okay, how fast is it going to grow? Well, it depends on how many are there, right? If you have fewer there, then it's not going to grow as much as if you have a large population. Money is like that, of course, right? It's easy. Sometimes you hear the expression, the rich get richer. It's very easy if you're already rich to make more money than it is if you're not as rich. Then it's not that easy to make as much money. So the rate of change is proportional to the amount present. This could also be a decay situation. Okay, example is could be population decay. A population sometimes decline, or radioactive decay for radioactive isotopes of elements or substances. Okay, the rate of change is proportional to the amount present. Okay, so if you're giving out radioactivity, okay, some substance is giving out radioactivity, say, what's the rate at which it's spitting out its radiation? Well, it depends how much is there. Obviously, the more that you have, the larger the rate, but the smaller amount that you have, then the smaller amount of radiation, right? All right, now, so I say this, but there aren't that many homework problems that involve that, okay? This is sometimes called a differential equation, okay? A differential equation is an equation that has one or more derivatives. As you can see, there's a derivative here. You can take an entire class called differential equations. Okay, in fact, normally at a community college, the highest math class that's offered is differential equations. where the entire semester you study equations that have one or more derivatives. Okay, so at CSM, that would be Math 275. The highest math course that's offered normally at a community college is a course in differential equations. Okay, well, you could solve this differential equation. You end up with this, and I think you've seen this before. So theorem 2, this is a big one. Okay, and again, it's on page 237. Definitely put this on your cheat sheet. Y of t is y0 e to the kt. Okay, these are solutions to the differential equation. So if something behaves this way, where dy dt is equal to k times y, okay, then the solutions are y of t equals y0 e to the kt. Now, y of 0 is the initial amount, beginning amount. Sometimes it's just listed as c as a constant. Y of t is the amount after a certain amount of time. We know E. K is a growth or decay constant. Many of our problems, we have to solve for that. Very few problems do you actually give that to you, but normally you have to solve for that. And T is, of course, time. Now, T, say, what are the units of time? It depends. You have to read the problems. So time could be measured in hours, minutes, seconds, years, weeks. It just depends on what the word problem says. Okay, so y of t is y0 e to the kt. And I want to emphasize that sometimes you'll see different letters here. You might see a of t is a0 e to the kt. A is for amount. Okay, you don't have to write any of this down, and I'll show it to you also, but they could change this letter and this letter instead of y. I've seen n for number. N of t is n0 e to the kt. Just so you know that they're really all the same. So y, a for amount, sometimes p for population, p of t, p0. So whatever letter they give me, it doesn't really matter. You don't have to write them all down. It's the same thing if they give you a different letter here and a different letter here. It's really the same equation, but this won't change in general. The e to the kt is pretty much set. But I've seen y of t and y0, a of t and a0 for amount, p of t and p0 for population, n of t, n0 for number, y just because, you know, we're used to y as a function of x or t, but they're all pretty much the same equation. Okay. So I'll show you a little bit of background theory before we get started. All right, I have here y equals c e to the kt. Okay, c is like the y0, but I'm specifically putting c here for a reason. Okay, otherwise everything looks the same, right? Y and y0. Okay, let's find a derivative. Now, dy dt, rate of change of y with respect to time. If I write it like that, it looks like a bunch of letters, but c is a constant, k is a constant. So let's take the derivative. So how do you differentiate c e to the kt? Well, you put down c e to the kt, and by the chain rule, it's times the derivative of kt, which is k. If I clean it up a little, it looks like k c e to the kt, and that c e to the kt is the same as my original y. So you can see that's where they came up with the differential equation, so-called dy dt is equal to k times y. Okay, so I have there the language. The rate of change is proportional to the amount present. Rate of change, dy dt, proportional, k, to the amount that's already present, y. Okay, so that matches that differential equation that they had. Box number 1, dy dt is equal to ky. Right? You're not responsible for this. I'm responsible for this. I'm just showing this to you. You're responsible for working all these problems out, which I'll do in just a minute. Okay, but just to show you where it came from. Okay. You can actually go backwards, okay, and you'll solve stuff like that if you were to take a course in differential equations. But you could start from dy dt equals ky and then work back to this, y equals c e to the kt. Okay. Now, here are variations of the same thing. So as I said, The book writes it like this: y of t equals y0 e to the kt. They have y parentheses 0. It's more compact to write the 0 as a little subscript. I'm going to write it as y sub 0 with a subscript, like so. It's the initial amount. Okay, so it's the amount that you start off with. So y of t equals y0 e to the kt. So I'm going to write down here initial amount. If I can get my pen to work here. Initial amount. Y of t is y0 e to the kt. So y0 is the initial amount. That always goes here. The new amount goes here. Sometimes they give it to you, sometimes they don't. You know E, that's the base for natural logs, it's 2.718, blah, 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 blah. K is a constant. Normally we'll solve for it. It's either a positive or a negative. Positive if it's a growth, negative if it's a decay. And T is time. Okay. And as I mentioned before, here are variations of the same thing. So you can write it or not. A for amount. A of t equals A0 e to the kt. It means the exact same thing. Okay. P for population. P of t equals P0 e to the kt. It still means the same thing. So don't think it's something different. So that letter and that letter might be different. It could be Y and Y, A and A, P and P. I could also have an N, but that's good enough. Okay, and I think you've seen these kind of problems before, so we'll be working our way through it. Okay, make sure you have your calculator ready for these and be ready to use your log and your ln and e to the x button. So we're hardly ever going to use log base 10 or 10 to the x anymore. We're going to be doing ln and e to the x much more often. Okay. All right, so I'll just show you how some of this works. And here we go. Okay, so number one. And this gets a little clumsy. If we were meeting on campus, I could project this on the document camera and still use the whiteboard, but I can't do that now. So I have to bounce back and forth. A population of protozoa developed, number one, with constant relative growth rate of 0.7944 per member per day. So that's the K, that's the constant. On day 0, the population consists of 2 members. That's the initial amount. Find the population after 6 days. Okay. So here's the important data. The constant they tell me, K, is 0.7944. The initial population is 2. I just pretty much just plug everything in. Okay. So it's a straight plug-in. So P of 6, I'm plugging in 6. P0 is 2. E to the K, T. Okay. Yeah, somebody made a comment that my mic might be lagging. I'm not sure, and I can't really do anything about it. But I think you can still hear me. If you all can't hear me, then let me know or something, but I'm assuming you can all still hear. I've checked the recordings. The recordings are still listenable, if I can coin such a word. You can still kind of listen to them. Anyway, so this one's just straight plug-in. The initial amount was 2 protozoa. The constant was 0.7944, and the time was 6. So I just plug everything in and see what happens. Okay, so if you punch it in your calculator, now for stuff like population, you always round to the nearest whole number. So the nearest whole number was 235. Okay, and let me try to demonstrate that. Okay, so, and you should try this on your own too. 2 second function e to the x. Now to get e to the x, second function natural log, e to the, now when it's like this, you have to put this in parentheses. If you don't, the calculator might do this and then take the result and multiply it by 6. So I'm going to go parentheses 0.7944 times 6. Okay, so there we go. So there's how I typed it. 2e exponent parentheses 0.7944 times 6. And I see 234.99 rounded to 235. Again, so population rounded to the nearest whole number. Population of protozoa, bacteria, people, animals, whatever. Don't leave out as fractional amounts. You should have a whole number. Oh, and a quick reminder, some of your calculators, when you do any function like exponential, it automatically gives you the left paren, which mine doesn't. So here, I'll show you. The 2e. Okay, you see my calculator doesn't automatically give me the left parenthesis, but some of you it does. So let me hit my parenthesis. Some of you on your calculator, it automatically does that. So if it does that, you just have to make sure you close it. But everybody has to do this anyway. So 0.7944 times 6, close parentheses, like that. And then of course you should get the same thing. Okay, now watch out, do not do this. So if you have a calculator like mine, it might be a little bit of disadvantage if you do this. So watch out for this. I'm going to go ahead and show you this. 0.7944 times 6. Okay, I suspect this is not going to work. Let me see. Yeah, different answer. See what happens if I didn't put parentheses? By order of operations, the calculator treated, okay, so the calculator said, here's exponential and multiplication, right? So which is higher in priority? Exponent. So it did the e to the 0.7944, got that answer, and then multiplied that answer by 6, which is not the same thing as putting parentheses. So you have to make sure it's e to the whole thing. So way back to our expression, right? Like this, it's e to the parentheses, the whole thing. Okay. If you go like this, the calculator treats it as 2 times this times 6. You might as well just do 2 times 6, which is 12. That way. Or like this would be like the 6 comes down. Suppose I did 2e to blah, 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 and then down below times 6. Okay, that would be the interpretation of this, which you don't want to do, right? So that's why you need parentheses around the whole thing. Okay. All right, number 3. So that was a pretty easy one. You just plug everything in. Now some more where you have to think a little bit more. Okay, 3, a bacteria culture initially contains 100 cells. Okay, that's my initial amount. And so I have to kind of bounce back and forth here. It'd be a lot easier if we met on campus and I could just leave the book there and use the whiteboard, but I can't. So initial amount is 100. Okay, and then it says after an hour, the population has increased to 420. So 420 goes on the left-hand side. So here's my formula. A of t is A0, e to the kt. You could use y, you could use p. Okay, so 100 goes here, 420 goes here, 1 goes here because it says 1 hour, right? And I have to raise this up a little bit maybe. All right, so A, B, I'll just do them all. Find an expression for the number of bacteria after t hours, find a number of bacteria after 3 hours, find the rate of growth when the population reaches 10,000, blah, 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 blah. Okay. All right, so here's how we find the expression. 420 goes here, 100 here, e to the k times t, which is 1. Okay, so I plug in 1. And of course, when you plug in 1, that's easy. All right, divide both sides by 100. Okay, I will make the assumption you've seen this before. This should not be the first time you've seen it. You should have seen it in pre-calc, maybe even in intermediate algebra. So divide by 100. I've got 4.2 equals e to the k. How do I get rid of the e? Take the natural log of both sides. Okay. When I do the ln, that knocks out the e, so I get my k. So k is natural log of 4.2 and 1.43508. Okay. And I'm going to show it to you on this type of calculator also. So this is, most calculators are like this, the standard calculator where you can type it in just as that. So what was it again? ln 4.2, ln 4.2. So I literally type ln 4.2, 1.43508, which I rounded it off. Okay. Again, some of you, when you hit ln, it automatically comes up with the left paren, like that. So you should close it with the right paren. Okay. Now, if you have just a regular scientific calculator, this is, the bottom of the budget type of calculator, you have to go backwards. Okay, so backwards meaning you have to do 4.2 ln. Okay, I'm trying to catch all of you for different kinds of calculators. So you just experiment, just check if yours is a forward type of calculator or the backward type of calculator where you have to go backwards. So this calculator, you actually have to go 4.2 first, 4.2, and then hit your ln button. And of course you get the same answer, 1.43508, blah, 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 blah. Okay, so just experiment. Some calculators you have to go backwards, like that. All right, so I found the K, put that K back up over here. So here's the answer to part A. Come up with an expression for the way this thing grows. So A of t is 100 e to the 1.43508 t. Okay. Now part B, 3B, 3 hours. I just plug in 3. Easy. Let's plug in 3. So A of 3 is 100 e to the 1.43508 times 3. And if you do it the right way, 7409 roughly. Okay, 100 e to the, okay, and by the way, hopefully if you have a calculator that has an answer button, rather than typing this in all over again, I can just say answer times 3. Okay, so parentheses, second function, answer, ANS. Can you see what I did? When I type 100e to the answer times 3, to the calculator right now, answer stores the last result that you got. So that answer button is the same thing as if I type 1.43508452529 or whatever. Okay, 7408.8, rounded off to 7409. All right, C, I messed up the first time, but what's new? C, find the rate of growth after 3 hours. That's where you use the differential equation. This one, page 237. dy dt equals k times y. Okay, so after 3 hours, the answer to part B was 7409. So formula is K, the K which I got was 1.43508, whatever, times the amount. The amount we now know is 7409. So I just left it like that. You can punch that on your own later. Okay, but dy dx, or you could say dy dt actually. Yeah, I guess dy dt is more appropriate. So the formula is K times y. So the K we now know is 1.43508. And the y after 3 hours, so we needed the answer to part B to get that, right? So 7409 goes right there. So just multiply it out. Looks like it's about 10,000 maybe. I'm just guessing there. All right. And then the last part is a when question, W-H-E-N. D, when will the population reach 10,000? That's the new amount. So I plug in 10,000 for the new amount in that case. So 10,000 goes right here. 10,000 equals 100 e to the 1.43508 t. And raise it up so you can see a little bit better. Divide both sides by 100. 10,000 divided by 100 is 100. So I have 100 equals e to the 1.43508 t. How do I get rid of the e? ln, natural log both sides. So when you do the ln and the e cancel out. So I have natural log of 100 is all that. Natural log of 100 is 1.43508 t. Divide both sides by 1.43 blah, blah, blah. 3.21 hours. Time you can give as a decimal or fraction. Okay, so again, for population, always round to the nearest whole number, even if it doesn't say so, right? You can't have fractional people, right? Fractional animals, fractional bacteria, but time, you can have a fraction or decimal, so 3.21. Okay, and I'll try it on a backward calculator type. So you folks that have a regular scientific calculator, ln 100, you'd have to go 100 first, and then ln, my ln button is over here, it looks like. Okay, and then I'm supposed to divide it by what? 1.435, so divided by 1.43508 equals 3.2089, which rounds off to 3.21. So 3.21 hours. So there's my answer. Okay, and yeah, let me go ahead and raise this up again for focusing purposes, for at least everything that I've need to do today. There's that. There's that. And hopefully this is more readable. Oh, forget that. Right over there. And yeah, this one, which I haven't even done yet, but I'll do in a second. But at least I can show it to you raised up because I have to put it down in just a second. Yeah, okay. So it looks like I was going to do number 7 next. Okay, so let's look at 7, please. All right, so the examples that we have right now are growth. And let me do some decay ones. Number 7. Okay, so just a quick word. Number 5, somewhat similar. Okay, they're giving you a population in all these years, 1750, 1800, 1850, blah, 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 blah. Okay, so just throw it into the formula and hopefully you can get it from there. Okay, so I showed you 2 examples of growth. Now I'm going to show you 2 examples of decay. So 7. Experiments show that the chemical reaction N2O5 goes to 2NO2 plus half O2, takes place at 45 degrees C, blah, 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 blah. Here's the corresponding differential equation. Okay, when they put the brackets there, okay, and you chemistry people know that, that's a concentration of N2O5. There's dinitrogen pentoxide, I guess. Okay. Notice they put the negative on this side. I'm not sure why they did that. There's an extra hoop to jump through. Multiply both sides by -1, and it's over here. So rate of change of the concentration of N2O5 is -0.0005 times the concentration of N2O5. What they're really giving you is this differential equation. Number 1 on page 237. Okay, so the constant K is -0.0005. Okay, so as time goes by, the concentration of dinitrogen pentoxide decreases as this chemical reaction goes through. Okay, so again, this bracket there, it's not a math symbol, it's a concentration symbol used in chemistry, and you chemistry people know that. Okay, and this might be referred to as molarity. Some of you know what that means. Okay, molarity, okay, moles of solute per liters of solution. You don't have to write that down. If you have no idea what I'm talking about, don't worry about it. It's just a concentration. Okay, but for some of you chemistry people know, just this is a concentration of a substance. Okay, and the rate of change of that substance is decreasing, and this is the amount. Okay, in a nutshell, K is negative 0.0005. There's a negative over here. Just multiply both sides by -1, and we put that over there. Okay, find an expression for the concentration of N2O5. Again, that's not a math symbol, it's a chemistry symbol. Okay, concentration normally expressed in molarity. You don't have to write that down, but some of the chemistry people know that. After T seconds of the initial concentration is C. All they're telling you is the initial amount is C. Okay, so how do you do that now? All right, so this is the chemical reaction. Okay, don't worry about it. Okay, it's balance. So some of the chemistry people know, the number of atoms on this side has to match the number of atoms on this side. So there's 1, 2 nitrogens and 1, 2, 3, 4, 5 oxygens and so forth. But that's for the chemistry department to worry about. We don't have to worry about it too much, but just thought I'd piggyback off of what some of you know from your chemistry class, right? All right, so as I was mentioning earlier, this means the K is negative 0.0005. Here's the equation that they gave us. Negative d N2O5 dt is 0.0005 N2O5. This is the concentration of N2O5. Multiply both sides by -1. That's the K, essentially. So what is the equation? A of t is C e to the negative 0.0005 t. So that's the equation that you want. So that's the answer to part A. Now they say, what's the initial concentration? I don't know. They don't tell us. In fact, all they tell us is C, right? So where am I? Here. Yeah, if you look at A at the top there, the initial concentration is C. So they don't say like 100 grams or 5 tons or 63 pounds, it just says C. So that's all we can do. B, how long will the reaction take to reduce the concentration of N2O5 to 90% of its original value? They don't even tell you the original value, but you can still do the problem. And here's how. Okay, so here's the answer to A. All right, now the original was C. The problem said 90% of the original value, 0.90 C. Okay. So what's C? Is it 1 gram or 2 milligrams or 1,000,000 tons? It doesn't matter. Just call it C. 90% of that is 0.90 C. And can you see what's going to happen? I'm just going to divide both sides by C and gone, 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 gone. Okay. So it doesn't matter what the C is, the answer would be the same. Okay, that's one important principle about radioactive decay or growth, okay, that the growth would be the same formula regardless of the initial amount. So if you said 90%, it doesn't matter if it's 90% of a tiny little speck, like 1 milligram, or if you've got millions and millions of tons of some substance, okay, this problem would still work out the same way because as you can see, the C's cancel out, provided that C is not 0, right? You can't divide by 0, but stop and think about it. If C is 0, concentration is 0, you don't have any of the substance, so there's nothing to talk about, right? So we'll make the very good assumption that this is non-zero, divide by C, and it all cancels out. So yes, for this particular problem, you didn't actually need to know what was the initial amount. You work it out the same way. Just divide by C, and then you have 0.90 equals e to the negative 0.0005 t. These problems tend to work the same way. Like, how do you get rid of the e? Natural log, right? ln, they cancel out. ln of 0.90 is negative 0.0005 t. Divide both sides by negative 0.0005. Okay, and I got 211 seconds. Okay, and let me verify that. ln 0.90, you can just put 0.9, right? Again, those of you whose calculators automatically gives you the left paren, you got to close it with the right paren. I don't have to on mine, but let me see if I can show you. Can I squeeze that in? Yeah, some of your calculators, it goes like that, right? So you folks have to close it with the right parentheses. And then divided by, what was it again? Negative 0.0005, negative 0. Of course, that, you know, that leading zero is optional. Okay, negative 0.0005. 210.72. Rounded off to 211 seconds. Okay, I will let you leave it like that, but if you have something that's more than a minute, it's more natural to change it to minutes. Okay, since there are 60 seconds in a minute, then if I divide by 60, it's roughly 3.5 minutes. That seems more natural, right? To say 3.5 minutes as opposed to 211 seconds, right? 211 seconds, you kind of have to think in your brain, you know, how do I divide and stuff like that. Okay, so 211 seconds or 3.5 minutes. Of course, it's more natural to say 3.5 minutes. Okay. So this is a decay situation, and I'm going to show you one more decay situation involving half-life. Okay, so number 9. Okay, the half-life of cesium-137 is 30 years. Suppose we have a 100 milligram sample. Aha. So that 100 means that's my initial amount. That's my A0. Find the mass after T years. How much remains after 100 years? After how long will only 1 milligram remain? Okay, so I'll lose the book and just go through here. Do not use the 137 anywhere, and you chemistry people know this ahead of time, and some of you physics people maybe. Okay, cesium-137 names the particular isotope, as it's called, of cesium. It's one particular type of cesium, okay, where the number of protons stays the same, but the number of neutrons might change, okay, but it's still considered cesium. So some cesium is heavier than others, more massive, okay. So the atomic weight, the number of protons plus the neutrons, is about 137 for this particular cesium. Okay, and if you have absolutely no idea what I'm talking about, some of you know exactly what I'm talking about. If you have no idea what I'm talking about, don't worry about it. Cesium-137, just think of it, that's the name of the substance. Don't use the 137 anywhere. Okay. All right, half-life is 30 years. That means after 30 years, the substance decays to half the original amount, right? Half-life. Okay. So if I have 8 grams, after 30 years, it'll go down to 4 grams. However, after another 30 years, it doesn't go down to 0. It doesn't go down in a straight line. Okay. After another 30 years, the 4 becomes 2. And after another 30 years, the 2 becomes 1, and so on. Okay. That's the way radioactive decay works. Okay. So it's not in a straight line. Okay. All right. So yeah, again, I wish I could just keep the book up showing, but I can't. So you just have to take my word for it, I guess. Okay, half-life is 30 years. It says start with 100 milligrams. That's the left-hand side. That's the right-hand side here. A of t is A0, e to the kt. You could say y of t is y0, e to the kt. You're gonna have p of t for population, although population is kind of weird here because we're not doing, you know, people or protozoa. We're doing molecules or atoms. A of t is A0, 100, e to the kt. Now, it said half-life. I put 50 here. Why did I put 50 here? That's half of 100. Half-life is 30 years. That means if I plug in 30 for the time, I get half the amount, 50. Okay, and like I said, suppose this was 8. Then over here I would have put 4. If this was, you know, 2 million, over here I would put 1 million. It would all be exactly the same thing. And something else, suppose all they told you was C. This would be half C, 0.5 C, just like the previous problem. So you can still do the problem if it just says C. All right, so 50, where'd the 50 come from? Half of 100, e to the k times 30. Okay, and let me check the chat real quickly. All right. All right, so you're putting some answers on. I don't know what the answer is until I work it out. Okay, but I think I know what you meant after so many half-lives. So after 30 years, you'll have 50. After 30 more years, it'll be 25. After 30 more years, half of 25, 12.5, and so on. Okay, but anyway, that's getting off the topic here. So let's find decay. So divide by 100, 0.5. And by the way, yes, 50 but divided by 100 is a half. But if you're punching it in a calculator, it's probably easier to use 0.5 as opposed to 1/2. It's a little bit more clumsy. So 0.5 equals e to the k times 30, or 30k. These problems tend to be the same thing. How do you get rid of the e? ln, natural log both sides. Cancel the ln's. ln 0.5 is 30k. Divide by 30. K is ln 0.5 divided by 30, which is about negative 0.0231. And let me show it to you again. So those of you that have the slower calculator, the backwards type of calculator. So ln 0.5, you have to go backwards. So 0.5 first, and then hit ln. Just experiment with your calculator if you're not sure how it works. Okay. And then I'm supposed to divide it by 30. So divided by 30 equals negative 0.023104. I rounded up to negative 0.0231, as you can see. Or if you have, most calculators nowadays, you can just type it all at once. So ln 0.5 divided by 30. ln 0.5. Again, my calculator, you don't have to have the left paren, but if it automatically gives you the left paren, make sure you do the right paren first, right? And of course, there's the same answer, negative 0.0231, blah, 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 blah. Okay, so I'll make it negative 0.0231. So the answer to part A, give an equation for the way this cesium, was it? Cesium-137 or whatever decays. So 100, A of T is 100 e to the negative 0.231 T. Okay, then part B, 9B. How much remains after 100 years? I just plug in 100 for the time, right? Pretty straightforward. So A of 100, 100 e to the negative 0.0231 times 100. Looks like it's about 9.92, close to 10. Okay, and again, for order of operations, if you're going to type it in, put parentheses around this, I'm actually going to use my answer button again. And by the way, further on down the line, we're going to use this answer button a lot more. Okay, so let's see, what do I need? 100, second function, e, parenthesis. Okay, so in my calculator, the last result stored was at negative 0.023 stuff. So I'm just going to hit second function answer times 100. Makes it a lot faster. Okay, so again, by hitting answer, it's just like to the calculator, I typed in negative 0.023104, blah, 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 blah. And there it is, rounded off 9.92. Okay, and what object are we doing here? This is milligrams. So of course, give the units. Milligrams, you can have a fraction or decimal. Time, you can have a fraction or decimal. People, you don't leave answers with fractions or decimals. Okay, but you can have a fraction amount of milligrams. So 9.92. Okay, finally C, and then we're done. And we're out of time. And I'm pretty much done with the section, actually. So let's see. 9C, after how long will only 1 milligram remain? That's the new amount. So the left-hand side in the original formula, put 1 right there. 1 equals 100 e to the kt. So 1 equals 100 e to the negative 0.0231 t. Okay, again, negative because it's decay. Decay will end up with a negative constant. Growth will have a positive constant. Okay, divide by 100. 1 divided by 100 is 0.01. 0.01 equals e to the negative blah, blah, blah. Same old stuff. How do you get rid of the e? ln cancels out. ln of 0.01 is negative 0.0231 t. Divide both sides by negative 0.0231. And t is 199.35 years, roughly 200. Okay, and let me see if I can show that to you. So ln 0.01, ln 0.01 divided by negative. Again, watch out on my calculator. I think most calculators, this is how you get the negative. Don't use this button. This is for subtraction. You can tell the difference because this minus has the divide times minus plus. So you should say to yourself, oh yeah, these are the 4 arithmetic operations, right? So this is the one to get a negative. That's the subtraction button, right? So I go negative, right? And negative, what was it again? 0.0231. Negative 0.0231. Okay, so there, ln of 0.01 divided by negative 0.0231. So 199.358 or whatever. And my answer is in years. Okay, if you rounded this 200 years, that's fine. Okay, in this particular case. So 199.35 years is my answer. Okay. All right, folks, so I think I've shown you everything you need for this section. I showed you 2 growth and 2 decay. Let me raise this up again quickly. So I think that's all the time I needed. So you should be able to do the rest of the problems. There we go. So next time I'll start 3.9 related rates, word problems involving something called related rates. Okay. All right, I think that's about it. I'm going to stop this share. Let me check the chat real quickly. Otherwise, we're done. And I think I've caught up with the chat. I can read the chat a little bit later from there. Okay, that'll do it for today, folks. All right, so everybody have a good day, and we'll see everybody tomorrow. All right, okay, bye everyone. Have a good day.